Alum, älum, is both a specific chemical compound and a class of chemical compounds. The specific compound is the hydrated potassium aluminium sulfate with the formula Cal(So)4,212H2O. More widely, alums are double sulfate salts with the general formula Am(So)4,212H2O, where A is a monovalent cation such as potassium or ammonium and M is a trivalent metal ion such as aluminium or chromium. When the trivalent ion is aluminium, the alum is named after the monovalent ion. Chemical properties. Alums are useful for a range of industrial processes. They are soluble in water, have a sweetish taste, react acid to litmus, and crystallize in regular octahedra. When heated, they liquefy, and if the heating is continued, the water of crystallization is driven off, the salt froths and swells, and at last an amorphous powder remains. They are astringent and acidic. Uses. Industrial uses. Potassium alum is the common alum of commerce, although soda alum, ferric alum, and ammonium alum are manufactured. Alum has been used at least since Roman times for purification of drinking water and industrial process water. Between 30 and 40 ppm of alum for household wastewater, or often more for industrial wastewater, is added to the water so that the negatively charged colloidal particles clump together into flocks, which then float to the top of the liquid, settle to the bottom of the liquid, or can be more easily filtered from the liquid, prior to further filtration and disinfection of the water. Alum solution has the property of dissolving steels while not affecting aluminium or base metals, and can be used to recover workpieces made in these metals with broken tool bits lodged inside them, as considerable expense and/or effort may have gone into machining a specialist part. This can be a worthwhile exercise. Cosmetic alum in block form can be used as a blood coagulant. Styptic pencils containing aluminium sulfate or potassium aluminium sulfate are used as astringents to prevent bleeding from small shaving cuts. Alum may be used in depilatory waxes used from the removal of body hair or applied to freshly waxed skin as a soothing agent. In the 1950s, men sporting crew-cut or flat-top hairstyles sometimes applied alum to the hair as an alternative to pomade. When the hair dried, it would stay up all day. Alum's antiperspirant and antibacterial properties contribute to its traditional use as an underarm deodorant. It has been used for this purpose in Europe, Mexico, Thailand, throughout Asia and in the Philippines. Today, potassium or ammonium alum is sold commercially for this purpose as a deodorant crystal, often in a protective plastic case. Culinary alum powder, found in the spice section of many grocery stores, may be used in pickling recipes as a preservative to maintain fruit and vegetable crispness. Alum is used as the acidic component of some commercial baking powders. Alum was used by bakers in England during the 1800s to make bread whiter. This was thought by some, without adequate scientific grounds, to cause rickets. The Sale of Food and Drugs Act 1875 prevented this and other adulterations. Flame retardant solutions containing alum may be used to treat cloth, wood, and paper materials to increase the resistance to fire. Alum is also used in fire extinguishers to smother chemical and oil fires. Chemical flocculent alum is used to clarify water by neutralizing the electrical double layer surrounding very fine suspended particles, allowing them to flocculate. After flocculation, the particles will be large enough to settle and can be removed. Alum may be used to increase the viscosity of a ceramic glaze suspension. This makes the glaze more readily adherent and slows its rate of sedimentation. Taxidermy alum is used in the tanning of animal hides to remove moisture, prevent rotting, and produce a type of leather. Traditionally, treating hides with alum instead of tannic acid is called tawing and not tanning. The product is traditionally called parchment instead of leather. Medicine alum is used in the treatment of canker sores in the mouth, as it has a significant drying effect to the area and reduces the irritation felt at the site. Alum is the major adjuvant used to increase the efficacy of vaccines, and has been used since the 1920s. Alum has been used to stop bleeding in cases of hemorrhagic cystitis. Art alum is used to fix pigments on a surface, for example in paper marbling. Alum is an ingredient in some recipes for homemade modeling compounds intended for use by children. These are often called clay or Play-Doh, for the similarity to Play-Doh. History. In antiquity and the Middle Ages, the word älum occurs in Pliny's Natural History. In the 52nd chapter of his 35th book, he gives a detailed description, by comparing this with the account of Stopteria given by Dioscorides in the 123rd chapter of his 5th book. It is obvious the two are identical. Pliny informs us that älum was found naturally in the earth. He calls it sal sugarteri. Different substances were distinguished by the name of älum, but they were all characterized by a certain degree of astringency, and were all employed in dyeing and medicine, the light-colored älum being useful in brilliant dyes, the dark-colored only in dyeing black or very dark colors. One species was a liquid, which was apt to be adulterated, but when pure it had the property of blackening when added to pomegranate juice. This property seems to characterize a solution of iron sulfate in water, where a solution of ordinary alum would possess no such property. Pliny says that there is another kind of alum that the Greeks call Jiteshn, and which splits into filaments of a whitish color. For the name Jiteshn and the mode of formation, it appears that this species was the salt that forms spontaneously on certain salty minerals, as alum slate and bituminous shale, and consists chiefly of sulfates of iron and aluminium. In some places the iron sulfate may have been lacking, so the salt would be white and would answer, as Pliny says it did, for dyeing bright colors. Pliny describes several other species of alum, but it is not clear as to what these minerals are. The alum of the ancients, then, was not always the same as the alum of the moderns. They knew how to produce alum from alunite, as this process is archaeologically attested on the island Lesbos. This site was abandoned in the 7th century but dates back at least to the 2nd century CE. Native alum from Melos appears to have been a mixture mainly of alunigine Al. 2, so 4, 317H2O with alum and other minor sulfates. The western desert of Egypt was a major source of alum substitutes in antiquity. These evaporites were mainly Feel. 2, so 4, 422H2O, MgAl. 2, so 4, 422H2O, Nal. So 4, 26H2O, MgSO. 47H2O and Al. 2, so 4, 317H2O. Contamination with iron sulfate was greatly disliked as this darkened and dulled dye colors. They were acquainted with a variety of substances of varying degrees of purity by the names of missy, sori, and chalcanthum, as alum and green vitriol were applied to a variety of substances in common, and as both are distinguished by a sweetish and astringent taste. Writers, even after the discovery of alum, do not seem to have discriminated the two salts accurately from each other. In the writings of the alchemists we find the words missy, sori, chalcanthum applied to alum as well as to iron sulfate, and the name atramentum sartorium, which one might expect to belong exclusively to green vitriol, applied indifferently to both. Various minerals are employed in the manufacture of alum, the most important being alunite, alum schist, bauxite and cryolite. Alchemical and later discoveries and uses. In the 18th century, Johann Heinrich Pott and Andreas Sigismund Markgraf demonstrated that alumina was a constituent. Pott in his Lithogeognosia showed that the precipitate obtained when an alkali is poured into a solution of alum is quite different from lime and chalk, with which it had been confounded by G. E. Stahl. Markgraf showed that alumina is one of the constituents of alum, but that this earth possesses peculiar properties, and is one of the ingredients in common clay. He also showed that crystals of alum can be obtained by dissolving alumina in sulfuric acid and evaporating the solutions, and when a solution of potash or ammonia is dropped into this liquid, it immediately deposits perfect crystals of alum. Torbern Bergman also observed that the addition of potash or ammonia made the solution of alumina in sulfuric acid crystallize, but that the same effect was not produced by the addition of soda or of lime, and that potassium sulfate is frequently found in alum. After M. H. Klaproth had discovered the presence of potassium in leucite and lepidolite, it occurred to L. N. Flocculent that it was probably an ingredient likewise in many other minerals. Knowing that alum cannot be obtained in crystals without the addition of potash, he began to suspect that this alkali constituted an essential ingredient in the salt, and in 1797 he published a dissertation demonstrating that alum is a double salt composed of sulfuric acid, alumina, and potash. Soon after, J. A. Chaptal published the analysis of 4 different kinds of alum, namely, Roman alum, Levant alum, British alum and alum manufactured by himself. This analysis led to the same result as Flocculent. Early uses in industry. Egyptians reportedly used the coagulant alum as early as 1500 BC to reduce the visible cloudiness in the water. Alum was imported into England mainly from the Middle East, and, from the late 15th century onwards, the Papal States for hundreds of years. Its use there was as a diaphix for wool. These sources were unreliable, however, and there was a push to develop a source in England, especially as imports from the Papal States were ceased following the excommunication of Henry VIII. In the 13th and 14th centuries, alum was a major import from Phocaea by Genoans and Venetians and later by Florence. After the fall of Constantinople, alunite was discovered at Olfa in the Papal States. The textile dyeing industry in Bruges, and many other locations in Italy, and later in England, required alum to stabilize the dyes onto the fabric and also to brighten the colors. With state financing, attempts were made throughout the 16th century, but without success until early on in the 17th century. An industry was founded in Yorkshire to process the shale, which contained the key ingredient aluminium sulfate, and made an important contribution to the Industrial Revolution. One of the oldest historic sites for the production of alum from shale and human urine of the Peak Alum Works in Ravenscar, North Yorkshire. By the 18th century, the landscape of northeast Yorkshire had been devastated by this process, which involved constructing 100-feet stacks of burning shale and fueling them with firewood continuously for months. The rest of the production process consisted of quarrying, extraction, steeping of shale ash with seaweed in urine, boiling, evaporating, crystallization, milling and loading into sacks for export. Quarrying ate into the cliffs of the area, the forests were felled for charcoal and the land polluted by sulfuric acid and ash. Production from alunite. In order to obtain alum from alunite, it is calcined and then exposed to the action of air for a considerable time. During this exposure, it is kept continually moistened with water, so that it ultimately falls to a very fine powder. This powder is then lixiviated with hot water, the liquor decanted, and the alum allowed to crystallize. The alum schists employed in the manufacture of alum are mixtures of iron pyrite, aluminium silicate and various bituminous substances, and are found in Upper Bavaria, Bohemia, Belgium, and Scotland. These are either roasted or exposed to the weathering action of the air. In the roasting process, sulfuric acid is formed and acts on the clay to form aluminium sulfate. A similar condition of affairs being produced during weathering. The mass is now systematically extracted with water, and a solution of aluminium sulfate of specific gravity 1.16 is prepared. This solution is allowed to stand for some time, and is then evaporated until ferrous sulfate crystallizes on cooling. It is then drawn off and evaporated until it attains a specific gravity of 1.40. It is now allowed to stand for some time, decanted from any sediment, and finally mixed with the calculated quantity of potassium sulfate well agitated, and the alum is thrown down as a finely divided precipitate of alum meal. If much iron should be present in the shale, then it is preferable to use potassium chloride in place of potassium sulfate. From clays or bauxite. In the preparation of alum from clays or from bauxite, the material is gently calcined, then mixed with sulfuric acid and heated gradually to boiling. It is allowed to stand for some time. A clear solution drawn off and mixed with acid potassium sulfate and allowed to crystallize. When cryolite is used for the preparation of alum, it is mixed with calcium carbonate and heated. By this means, sodium aluminate is formed. It is then extracted with water and precipitated either by sodium bicarbonate or by passing a current of carbon dioxide through the solution. The precipitate is then dissolved in sulfuric acid, the requisite amount of potassium sulfate added, and the solution allowed to crystallize. Types. Many trivalent metals are capable of forming alums. The general form of an alum is AmAii2NH2O, where A is an alkali metal or ammonium, MIii is a trivalent metal, and N often is 12. In general, alums are easier formed when the alkali metal atom is larger. This rule was first stated by Locke in 1902, who found that if a trivalent metal does not form a cesium alum, it neither will form an alum with any other alkali metal or with ammonium. Double sulfates with the general formula A, 2SO, 4B, 2SO, 4, 324H, 2O are known, where A is a monovalent cation such as sodium, potassium, rubidium, cesium, or thallium, or a compound cation such as ammonium NH+, 4 methylammonium CH, 3NH+3 hydroxylammonium HONH+3 or hydrazinium N, 2H+. 5B is a trivalent metal ion such as aluminium, chromium, titanium, manganese, vanadium, iron, cobalt, gallium, molybdenum, indium, ruthenium, rhodium, or iridium. Analogous selenates also occur. The specific combinations of univalent cation, trivalent cation, and anion depends on the sizes of the ions. For example, unlike the other alkali metals, the smallest one, lithium, does not form alums, and there is only one known sodium alum. In some cases, solid solutions of alums occur. Alums crystallize in one of three different crystal structures. These classes are called alpha, beta and gamma alums. Potash alum, aluminum, potassium sulfate, potash alum, Cal, So, 4,2,12H2O is used as an astringent and antisepsis in various food preparation processes such as pickling and fermentation, and as a flocculent for water purification, among other things. A common method of producing potash alum is leaching of alumina from bauxite, which is then reacted with potassium sulfate. As a naturally occurring mineral, potash alum is known as alum. Other potassium aluminium sulfate minerals are alunite cal So 4,2,2L3 and kalinite cal So 4,2,11H2O, Soda alum null So 4,2,12H2O mainly occurs in nature as the mineral mendozite. It is very soluble in water, and is extremely difficult to purify. In the preparation of this salt, it is preferable to mix the component solutions in the coal, and to evaporate them at a temperature not exceeding 60 degrees Celsius. 100 parts of water dissolve 110 parts of sodium alum at 0 degrees Celsius, and 51 parts at 16 degrees Celsius. Soda alum is used in the acidulant of food as well as in the manufacture of baking powder. Ammonium alum, and H4Al So 4,2,12H2O, a white crystalline double sulfate of aluminium, is used in water purification, in vegetable glues, in porcelain cements, in deodorants, in tanning, dyeing and in fireproofing textiles. Chrome alum, KCr So 4,2,12H2O, a dark violet crystalline double sulfate of chromium and potassium, was used in tanning. Selenate containing alums. Alums are also known that contain selenium in place of sulfur in the sulfate anion, making selenate selenium monoperoxide -4 instead. They are called selenium or selenate alums. They are strong oxidizing agents. Aluminium sulfate is referred to as papermaker's alum. Although reference to this compound as alum is quite common in industrial communication, it is not regarded as technically correct. Its properties are quite different from those of the set of alums described above. Most industrial flocculation done with alum is actually aluminium sulfate. Solubility. The solubility of the various alums in water varies greatly, sodium alum being readily soluble in water, while cesium and rubidium alums are only sparingly soluble. The various solubilities are shown in the following table. At temperature T, 100 parts water dissolve related compounds. In addition to the alums, which are dodecahydrates, double sulfates and selenates of univalent and trivalent cations occur with other degrees of hydration. These materials may also be referred to as alums, including the undecahydrates such as mendozite and kalinite, hexahydrates such as guanidinium CH6 and +3, and dimethyl ammonium CH3, 2NH+2 alums, tetrahydrates such as goldachite, monohydrates such as thallium, plutonium sulfate and anhydrous alums. These classes include differing, but overlapping, combinations of ions. A pseudo alum is a double sulfate of the typical formula ASO 4B2 So 4,322H2O, where A is a divalent metal ion such as cobalt, manganese, magnesium or iron, and B is a trivalent metal ion. A tartan salt is a double sulfate of the typical formula A2SO 4BSO 46H2O, where A is a univalent cation, and B a divalent metal ion. Double sulfates of the composition A2SO 42BSO 4, where A is a univalent cation and B is a divalent metal ion, are referred to as langbinides after the prototypical potassium magnesium sulfate.